Hello everyone and welcome back. In this video, we will discuss the simulation of a constant power load in LTSpice, PSPICE and PySpice. Constant power loads often arise in the context of power supply systems. I would like to thank Alan for suggesting this topic as an interesting idea to explore. As suggested in the comments ask for how to simulate a constant power load in PySpice. Before we look at PySpice, we will first look at LTSpice in detail. In LTSpice, there are three main ways to simulate a constant power load. The first method is to use a nonlinear resistor as a constant power load. The theory behind this is straightforward. Recall that for a resistor, voltage is given as the product of the resistance and the current, and the power dissipated in a resistor is given as V squared over R. Thus, if we set the value of the resistor equal to V squared over power, we can simulate a constant power load. This is shown here, where V out represents the voltage across the resistor. Setting the resistor value this way has a drawback that when the voltage across the resistor is very small, the current drawn by the resistor will be very large. To prevent this unrealistic behavior, we can use an if statement. In this case, if the voltage is less than 1 volt, then the resistor defaults to a constant fixed value, R min. Otherwise, it behaves as a constant power load. This is the same circuit in LTSpice. We have the nonlinear resistor here. We have defined a node here, so we can use the voltage across the resistor to set the resistor value. We have defined R min and power as global parameters. We are running a DC sweep simulation. We can simulate. When we bring the cursor over the node, the cursor shape changes to a voltage probe and we can plot the voltage across the resistor. When we bring the cursor over the symbol of the resistor, the cursor shape changes to a current probe and we can plot the current through the resistor. Finally, on a Windows machine, if we press the Alt key and bring the cursor over the resistor, the cursor shape changes to a power probe and we can plot the power dissipated in the resistor. In addition, we can right-click, add trace, and we can plot the resistance, which is V out over the current through the resistor. We can see that when the voltage is less than 1, the element is acting like a fixed resistance having value 40 ohm. Otherwise, the element is acting as a constant 25 watt load. This method of simulating a constant power load is not portable to other common simulators. This is because in LTSpice, when we set the value of R as an expression, the resistor quietly defaults in the background to a B or behavioral source. Thus, it is better to use a B source directly. In LTSpice, two types of B sources are available: an arbitrary behavioral current source and an arbitrary behavioral voltage source. More information about these sources is available at this link here. If you're interested, please check out these links. We can use either of the B sources and set the desired power directly as shown here. For instance, here we are using the behavioral current source and we're setting the power as 20 watts directly. The parameter VPRX over is used to prevent the current drawn from blowing up when the voltage is close to zero. More information about this parameter is available at this link shown here. When we simulate, we can take a look at the results. We can plot the voltage, the current, and the power. We can see that this B source is acting as a constant 20 watt load for voltages greater than 1 volt. This second method of simulating a constant power load is the simplest approach in LTSpice because we set the desired power directly, but unfortunately it is not portable to other common simulators. This is because the B source models in PSPICE and NGSpice do not accept the power as an input. The third method to simulate a constant power load in LTSpice is to use a behavioral current source and select its magnitude appropriately. The theory behind this method is also straightforward. Recall that for a resistor, the power dissipated is V times I, hence the current is given by power divided by the voltage. Thus, if we set the magnitude of the behavioral current source as I is equal to power divided by voltage, we can simulate a constant power load. However, this simple expression blows up when the voltage is close to zero. We can try to prevent the current from blowing up by adding a +1 factor to the denominator as shown in this statement, but the current may still be very large and impractical. We can get better models as follows. This statement defines a B source to behave like a constant power load as long as the current is less than some maximum value, which can be defined as a global parameter. This statement defines the B source to act as either a resistor having a minimum Rmin value or a constant power load. In this model, the transition between the two modes is abrupt and is governed by the min command. This statement defines a B source to have a smoother transition between the constant power and the minimum resistance modes. This statement defines a B source which behaves like a constant power load as long as the current drawn is within a practical defined limit. Finally, this last statement defines a B source which can act as a constant resistor if the voltage is less than 1, or a constant power load, or a constant current load if the current drawn exceeds I max. Any of these statements can be used depending upon the purpose of simulating a constant power load. Please pause the video now if you wish to study these in more detail. This is the same circuit in LTSpice. Here we are modeling the B source to act as a resistor having value 15 ohm when the voltage is small, and as a 50 watt constant power load when the voltage is large. When we simulate, we can obtain the results. We can look at the voltage, the current, the power. Also, we can add trace to look at the resistance. We can see that when the voltage is small, the B source is acting as a constant 15 ohm resistance, And when the voltage is greater than about 25 volts, then it's acting like a constant power load. This third method of using a behavioral current source to model a constant power load is portable to other simulators such as PSPICE and PySpice. Let's take a look at that. In PSPICE, we can use the Gvalue behavioral current source as a constant power load. Note that a resistor and other dependent sources in PSPICE must have a numerical value defined and do not accept expressions as input. This is showing the Gvalue behavioral current source set up to act like a constant power load having value 50 watts. The global parameters can be defined. Any of the valid B source modeled expressions can be used here. In this case, we are implementing this expression here. This is the same circuit in PSPICE. We have defined the global parameters. We have defined the node labels. We have placed the voltage and the current markers. We are running a DC sweep simulation. When we simulate, we can look at the voltage and the current. Also, we can go trace, add trace, and we can get the power by multiplying the voltage and the current. We can see that for voltages greater than 20 volt, this B source is acting as a constant 50 watt power load. We are now ready to implement a constant power load in PySpice. We can use a B circuit source. The syntax is shown here. We also use a 0 volt dummy source which is connected in series with the behavioral current source. This allows us to measure the current in the B source. We define the global parameters at the top and do the DC operating point simulation. At the end, we can display the set and the measured power. For the magnitude of the B source, we can use any valid current source model. Two options from earlier are shown here. Please note that in this syntax, the current I must be lowercase. Please pause the video now if you wish to study the syntax in more detail. This is the complete code in PySpice. The code is available in the video description as well as the comment section below. When we run this code, we get the results, and we can see that in this case, the B source is acting like a constant 15 watt power load as set. In this video, we have looked at 3 different methods to model a constant power load in LTSpice. The method of using a behavioral current source is portable to other simulators such as PSPICE and PySpice. In the near future, I hope to upload a video examining B sources in PySpice in more detail. Thank you for watching the video, and I hope that it is useful for your learning.